Okay, with this lecture, we are going to start discussing how to let transactions satisfy the asset properties. And so one of the first concepts we're going to discuss is known as serial equivalence. So there are concurrent transactions where multiple clients are executing transactions with the same server, and we need to prevent transactions from affecting each other. One of the simplest ways of achieving this is to just allow one client at a time to execute a transaction with the server. So a client comes in, acquires a lock on the server, for instance, and then executes its transaction. And then once it's done, the second client comes in, and so on and so forth. So this works as far as correctness is concerned, but it's pretty bad as far as performance is concerned. It reduces the number of transactions that are executing concurrently. And this is important because you want to allow more transactions to execute concurrently, because this increases the transactions per second metric. The higher the transactions per second you can support, the higher is the revenue of the company. For instance, if a flight booking website had a very low transactions per second, clients would just not use it because it would be a very slow system that would not be able to support more than one user at one time. And so you want to allow more concurrency. You want to maximize this metric, but at the same time, you also want to make sure that your system is correct. In other words, it maintains the asset properties. Okay, so that is the challenge overall in concurrency control. How do you increase the level of concurrency? How do you increase transactions per second? How do you allow more transactions and more transactions to execute concurrently while still not violating the asset properties for transactions? So therein comes the concept of serial equivalence, an interleaving of a transaction operation. Say you have two transactions and their operations are interleaved in a particular order. This is the actual order in which the operations occurred in the server itself. That particular interleaving is said to be serially equivalent if and only if the following conditions are true. There is some other ordering of those transaction operations. So this is the original interleaving. Maybe there is a different interleaving that looks like this. We call that interleaving as O prime, which gives the same end result as the original interleaving O. This means that the original interleaving O left the server objects in a particular state, and the fake make-believe O prime ordering that we have also leaves the server objects in exactly the same state. So they are indistinguishable from that viewpoint. But in this new ordering O prime, you have the transaction operations such that all the operations of any given transaction are consecutively, meaning they are together in this interleaving. This means that essentially the interleaving O prime, the fake make-believe interleaving, has each transaction execute one at a time. So a transaction comes in, it executes its operations in a batch, and then the next transaction comes in, it executes its operations in a batch, and so on and so forth. Because essentially we are saying that an interleaving O, which happen in real life, is serially equivalent if there is a parallel world in which if transactions had executed one transaction at a time, then the end result, as far as the servers are concerned, would have been the same as this original interleaving O. Okay, so even though the transactions overlapped and even interfered and interleaved with each other, the end result is the same as if the transactions had executed serially one transaction at a time. Okay, so the key here is that you are not able to distinguish the end results of the two, and so the interleaving is still serially equivalent, even though it's not actually serial. So how do you check for serial equivalence? Now an operation has an effect on the server if the operation is a write, and so the server object is then updated. The operation has an effect on the client, the return value, if the operation is a read. Okay, so we call these two as the effects of the operation, depending on whether it's a write or a read. Now two operations are said to be conflicting operations if their combined effect depends on the order in which they're executed. In other words, swapping their order will give you a different end result as far as the servers or the clients are concerned. For instance, if I have a read operation on an object X and a write operation on the same object X, for instance being executed by two different transactions, their ordering is going to make a difference. If the write came first, then the read will read this newly written value. However, the read came first, then it would read the old written value, and so the combined effect of these two operations really depends on the order in which they are executed. Similarly, a write and a read on the same variable, which is essentially symmetric as a read and a write. Also, a write and a write are conflicting because whichever write comes second, that value is going to stay for a while. Okay, that's the overriding value. However, two reads on the same object are not conflicting because as long as these are the only two operations we're talking about, The order in which they occur, whether the second read comes before the first read or whether the first read comes before the second read, it doesn't really matter. The end result is the same. The individual clients will get the same read value. Okay, so swapping them doesn't really make a difference, and so they are not conflicting operations. Also, operations on two different objects, x and y, whether they're read or a write, are non-conflicting. Here we are assuming their objects are, of course, independent of each other. But in that case, the operations of them are not conflicting because essentially objects don't interfere with each other. They are independent objects in and of themselves. So now that we know what conflicting operations are, we can say what the conditions are under which two transactions are serially equivalent. Okay, so given two transactions and a particular order of interleaving, that order of interleaving is said to be serially equivalent if and only if all pairs of conflicting operations where the pair contains one operation from each transaction is executed in the same transaction order for all the objects that the transactions access. So what this is saying is the following. Suppose I have two transactions, T1 and T2. I take a particular interleaving. I'm going to take all pairs of conflicting operations where one part of the pair comes from T1, the other part comes from T2. If the T1 part of the pair was executed first in that particular interleaving, then I'm going to mark that pair as T1 comma T2, okay, because the T1 part occurred first. However, if the T2 part of that pair occurred first in that interleaving, then I'm going to mark that as T2 comma T1. You mark all the pairs of conflicting operations with either T1 T2 or T2 T1 in this way, and then at the end all these pairs should be marked as either all T1 T2s or all T2 T1s. If either of these two conditions is true, then this particular interleaving is serially equivalent. Okay, essentially we're saying that it is equivalent to the case where if it's all T1 T2s, then it's equivalent to the case where the fake make-believe scenario where T1 executed completely first and then T2 executed. If there are some pairs which have T1 T2 and other pairs that have T2 T1, then these two transactions, or rather their interleaving, is not serially equivalent. So we need to see this in action. So let's go back to the two problems we discussed in the previous lecture, which were giving us trouble. The first is the lost update problem. Here, two transactions T1 and T2 were simultaneously trying to update a given variable, and one of their updates was getting lost, and instead of the seats going down from 10 to 8, it was only going down from 10 to 9. Okay, so what are all the conflicting operations here? Remember that a conflicting operation pair has to be a read-write or a write-write pair on the same object. So here's one example of a conflicting operation. Transaction T1 writes to the object ABC123, and transaction T2 reads from the object ABC123. Okay, so it gets seats. So this is a read-write pair on the same object ABC123. So that's a conflicting operation pair, and this operation pair has the T2 part of its pair occurring first in this particular interleaving, and so we mark that as a T2 comma T1 pair. Okay, so are there other conflicting operation pairs? Well, here's another conflicting operation pair, a write-write pair on the same object ABC123. Okay, so again here you have the T1 part of the pair occurring first, and so we mark this as T1 comma T2. There is another pair of conflicting operations, which is the get seats or a read on ABC123 by T1 and the write on ABC123 by T2. And once again, this is a read-write pair on the same object ABC123, and the T1 part of the pair occurs first, so we mark that as T1 T2. Here in this interleaving, you'll notice that there is one conflicting operation pair that has a T2 T1 tag, and another one, in fact two more, that have a T1 T2 tag, and that is why this particular interleaving is not serially equivalent. And so serial equivalence, or serial equivalence using the notion of conflicting operations, catches the lost update problem in this way. What about the other problem that we discussed, the inconsistent retrieval problem? Here again, if you remember, T1 was transferring 5 seats from one flight to another, and T2 was trying to sum up the total number of seats, and it was reading partial results. So here, what are the conflicting operations? You notice that there is a lot of reads from these two objects ABC123 and ABC789, and again a lot of reads. These are not conflicting with each other because they are only read-read pairs even on the same objects. But you do have some conflicting pairs. The write on ABC123 and the read on ABC123 are conflicting. So the T1 part, the write, occurs first in this interleaving, so we mark that conflicting pair as T1 comma T2. And once again, the write to ABC789 and the read from ABC789 from T1 and T2 respectively are conflicting pairs because this is a write-read pair. And here the T2 part of the pair occurs first, and so we mark that as a T2 comma T1 pair. And so obviously now you have two pairs of conflicting operations in this particular interleaving. The first being a right read pair that's marked as T1 T2, the second being a right read pair that is marked as T2 T1. And so this is not serially equivalent because we need all the conflicting operations marked as either T1 T2 or all are marked as T2 T1. Okay, so serial equivalence using the notion of conflicting operations also catches the inconsistent retrievals problem, as we have seen here. So what can we do about this? At the commit point of the transaction, what you do is that you check for serial equivalence using conflicting operations. You check for serial equivalence using all the other transactions in the system. You don't need to check really with all the other transactions. You only need to check with other transactions that overlapped with transaction T, transactions that had some overlapping with some of the operations of transaction T, either transactions that are already committed or transactions that are still going on. Okay, if you find that conflicting operations violate serial equivalence, for instance, if the conflicting operations violate serial equivalence and the other transaction involved is a transaction that is already committed, then you need to absolutely abort transaction T, because you cannot undo a transaction that is already committed. Okay, because you need durability. You want to make sure that a transaction that is committed has its updates reflected forever in the database. In that case, you would abort the transaction T. However, if the other transaction involved is a different transaction that is not yet committed, you might choose to abort that other transaction too. Okay, so the choice is up to you. No matter what you do, if you abort a transaction, you need to make sure that you roll back or undo any of the writes that T made to the server objects, so that the nothing property of the all or nothing guarantee is enforced, and that T aborted and none of its updates were reflected on any of the server-side objects. But really, what we're noticing here is that transactions are aborting, and that means wasted work, right? So the question arises, can you prevent violations from occurring at all?